Next is workbook question number 35. This is a common data question in which it is given that the double sideband suppressed carrier, double sideband full carrier wave is expressed V of t equal to 3 1 plus x of t cos omega naught t. If xt has Fourier transform x of f as shown in below figure, then the output spectrum for a coherent detector with local carrier amplitude equal to 1 and the phase error of 5 degree. So, in question number 35, we have AM signal V of t, this is 3 into 1 plus x of t cos omega naught t, and xt has Fourier transform x of f which is ranging from -fm to f and having amplitude 1. The output of output spectrum for a coherent detector with local carrier. So, we know that in case of coherent detector, we first multiply it with the same carrier. So, as a mixer or multiplier you can use so input is Vt and it is given that it is generated local carrier with amplitude 1 and phase error of 5 degree, because this is a coherent detector. So, it should have the same frequency is omega naught t. So, it should have the same frequency omega naught t, amplitude is 1 and the phase error is 5 degree, and then because it is synchronous detector, so the output of this mixer or multiplier will pass through the low pass filter. And then we get output. So, what is the spectrum at output, it is asked. So, as we have considered in case of synchronous detector, let us find the value of Yt and then we take the Fourier transform. So, x of t equal to 3 1 plus x of t multiplied with cos omega naught t and cos omega naught t plus 5 degree. So, when we multiply this, we get, this is the formula of cos A cos B. So, 2 cos A cos B, 1 plus x of t, 2 cos A cos B, cos A plus B, this is 2 omega naught t plus 5 and cos A minus B, that is cos 5. And when we multiply this term with these two, we get 3 by 2 cos 2 omega naught t plus 5 and 3 by 2 xt cos 2 omega naught t plus 5 and 3 by 2 cos 5 degree and 3 by 2 xt cos 5 degree. So, this is a high frequency term because it is having frequency 2f0 and it is also centered at 2f0 and plus minus fm. So, after low pass filter, this 2 will be rejected, suppressed by this low pass filter, it will not pass through the low pass filter, and it is having frequency fm and it is having frequency 0 because it is not given that there is a DC blocker. So, we have to consider the DC value as well because in the option the impulse is given to us, because we know that when f equal to 0 is present at the output, that means the impulse is present. So, if in the option impulse is given, then we have to consider that impulse because DC blocker is not given in the question. If the DC blocker was given in the question, then obviously we have to reject it, block it. So, we will get these two at the output. So, we get 3 by 2 cos 5 degree plus 3 by 2 x of t cos 5 degree. So, the cos 5 degree is common in both and the value of cos 5 is very 5 degree is actually very small. So, approximately we can consider the value of cos 5 degree as 1 because 5, that is very small, cos 5 is closely related to 1. So, this is approximately 1. So, we get y of t equal to, we are assuming it, then we are getting 3 by 2 plus 3 by 2 x of t, and it is asked in the question that the output spectrum. So, taking the Fourier transform, we get y of f equal to 3 by 2 delta f plus 3 by 2 x of f, and when we draw it 3 by 2, that means 1.5, this is 1.5, and x of f, it is given in the question, x of f is having amplitude 1, but here this is having amplitude 1.5 and ranging from minus fm to fm. So, we get this signal. We are getting impulse at 0 and of height 1.5. This is your y of f output spectrum, and according to the option, if we see that there are two options like this, which is option A and B, we having amplitude 1.5, but it is important to consider the impulse because the DC blocker is not given. So, according to that, the correct answer is option B. So, this was the question number 35. Now, in question number 36, the output spectrum for envelope detector assuming the maximum value of message signal is less than 1. So, the maximum value of message signal is less than 1, and we know that the standard expression for AM signal is given as AC 1 plus K into message signal into carrier signal. So, if we compare the expression of AM signal with the given expression, we find that the K is given as 1. And modulation index MA is defined as K into maximum value of message signal, in this case message signal is xt, and it is also given that the maximum value of x of t is less than 1, given maximum value of x of t, it is written like this in the question, is less than 1, because the k is 1 and the maximum value of xt is less than 1, that means the modulation index is less than 1. Okay, because the k is 1, so if the maximum value of message signal is less than 1, it means that the modulation index will be less than 1. So, if the modulation index is less than 1, the envelope detector works properly with the time constant making between 1 upon fc to 1 upon fm, it means it will give the message signal correctly, and the message signal is v of t 3 1 plus x of t cos omega naught t, and the message signal or the envelope here, if you find envelope here, so this is envelope 3 1 plus x of t, and this DC will be blocked. So, we will get 3 of xt because this is 3 and 3 x of t, and when the modulation index is less than 1, then we consider the envelope detector works properly, and this will be blocked by the DC blocker, and when this is blocked, then we get 3 of xt, and we have to find the spectrum. So, the spectrum y of f is 3 of x of f. So, finally we get x of f, that means our message signal, that is ranging from minus fm to fm. Previously it was having amplitude 1, but now this time 3 times of x of f. So, this will be the output spectrum. So, according to the option, the correct option is option C. See, because you can say that why we blocked the DC term, because here also there is no DC blocker written here, but the envelope detector has the property to block this DC value itself, because the envelope detector is designed in such a way that the DC will be blocked inside that envelope detector itself. So, that is why we considered the DC value blocked, and that is why we did not draw the impulse at f equal to 0. So, the correct answer is option A. So, answer for this particular option C. The correct answer is option C, because there is no impulse, right. So, option is option C. So next is workbook question number 37. Suppose that the modulating signal is m of t equal to 2 cos 2 pi fmt and the carrier signal is xc equal to ac cos 2 pi fct. Which one of the following is a conventional AM without overmodulation? So it is given that the message signal m of t is 2 cos 2 pi fct fmt, because this is message signal, and ct or carrier signal AC cos 2 pi fct xct. So message signal is having amplitude 2 and the carrier signal is having amplitude AC. Now there are 4 options given to us, and first option represents, let us find it what it represents. We have to make the modulation index less than 1, because it is asked that the modulation index, the signal should be without overmodulation. Without overmodulation means modulation index less than 1. What it represents? The message signal and the cos term. If the message signal and cos term represents double sideband, because the message signal is having a spectrum, suppose like this, minus FM to FM, this is the spectrum of M of F. Then if we multiply it by cos, then it shifts to the cosine frequency, and the cosine frequency is FC, so it will shift to the FC and minus FC, and there is no carrier at FC, there is no component present at FC, and that's why this is called double sideband suppressed carrier. But we have to find the AM signal. Conventional AM means double sideband full carrier. The carrier should also be present at the carrier frequency, and here the carrier frequency is FC, so there should be some component at FC, but there is no component at FC. That's why this cannot be our answer. So option A is eliminated. Now if I consider option D, it is given AC cos 2 pi fmt and cos 2 pi fct plus AC sin 2 pi fmt and sin 2 pi fct. Then in AC is common in both. So this is the formula of cos A cos B plus sin A sin B. So cos A cos B plus sin A sin B can be written as cos A minus B, cos A minus B. So it representing a lower sideband because it is having the frequency component less than the carrier frequency. So lower sideband means we can say this is the single sideband suppressed carrier. So it can also be not our answer, because again this is a single sideband suppressed carrier, we have to generate double sideband full carrier. Now let us consider, means option A and D are eliminated. Now let us consider option B. Option B, x of t is AC 1 plus mt cos 2 pi fct. So on comparing with the standard expression, our standard expression for AM is given by AC 1 plus k into mt cos 2 pi fct. On comparing these two, we get k equal to 1, and because it shows the expression of AM, because it is in the form of AC 1 plus k mt cos omega ct. That means this is a double sideband full carrier. This is double sideband full carrier. But now we have to check whether it is a overmodulated or without overmodulation. So without overmodulation, the modulation index should be less than 1, and the modulation index is given by MA equal to k into maximum value of mt, and the message signal is having maximum value 2. You can see from here the message signal is having maximum value 2, that is the amplitude of this sine wave, and this is 2. that means modulation index is greater than 1, it means this is over modulated. So our correct answer should be option C. Okay, because A, B and D have been eliminated, so our correct answer should be C. And if we want to calculate what is the modulation index in option C, then we can find it easily, because now we know that the modulation index is less than 1, and x of t, if I represent AC cos 2 pi fct plus AC by 4 mt cos 2 pi fct, and if I take this AC cos 2 pi fct common, then we get 1 plus mt by 4. And on comparing with the standard expression, we get k equal to 1 by 4, and the modulation index Ma is given by k into maximum value of mt, and k is 1 by 4, the maximum value of message signal here is 2. So we get modulation index 1 by 2, which is less than 1, that means without over modulation. So we can say the double sideband full carrier is option C without over modulation. Next one is question number 38. An AM wave represented by x of t equal to 10 1 plus 0.4 mt cos omega ct, where mt is defined by function f of z density function, and transmission efficiency we have to calculate. So it is given that x of t is 10 1 plus 0.4 mt cos omega ct, and the density function f of z equal to e to the power minus mod z. See, this is the question in which there are two concepts used. First is the concept of amplitude modulation, and other is the concept of random variable. So actually this question should be solved after studying the random variable, but because this question is given here and it includes the concept of AM, so I am discussing it here. But if you will not be able to understand this, then there is no tension about this, because you will understand when you study the random variable and the probability density function. Because many of you may be knowing the concept of random variable or the probability density function from the maths, that's why I assume that you might be knowing that, and that's why I am discussing it here. If you are not able to understand, then leave this question for now and study random variable first and then come back to this question, right? So the transmission efficiency we have to calculate, or power efficiency, and this transmission efficiency or power efficiency is given by eta is equal to k square Sm upon 1 plus k square Sm, where this Sm is known as mean square value. So let us find mean square value. Mean square value of message signal, that is the power of message signal, that is Sm, which is actually expectation of m square t, and it is given by integration from minus infinite to infinite the signal m square and its density function f of m dm, or here it is written in the form of z. So you can write f of z dz and z square, okay, because this is the message signal, that's why I am writing m square f of m dm. There is nothing but the change of variable only, so we can write like this. Now minus infinite to infinite, this is m square and e to the power minus mod m dm, or we can also write 2 times 0 to infinity, because this is even function. So m square e to the power minus m dm. Now we will integrate this, and the integration will be s of m equal to 2 times m square e to the power minus m divided by minus 1. Now positive and then negative, the differentiation of first term, that is 2m, and integration of second term, which is e to the power minus m upon minus 1 whole square, plus, now plus, minus, then plus, alternative negative and positive sign. So, negative then positive, and the differentiation of first term is 2, integration of second term is e to the power minus 1 whole cube, and limit from 0 to infinity, because now the differentiation of this term will be 0. So, there will be no further terms. Now, if I substitute the limits, so infinity, e to the power minus infinity is 0, e to the power minus infinity is 0, e to the power minus infinity is 0. Now, 0, when we put 0 for m, so this will be 0, this will be 0, because this is a multiplication with m. So, this is 0, this is 0, and when we put 0 here, we get e to the power 0, that is 1, and 2 upon minus 1 whole cube, that means minus 2 upon 1, and because we are substituting the lower limit, we will be having plus sign here. So, it means that we get the value 4, because this is the lower limit, right. Once I write 0 minus lower limit 2 upon minus 1 whole cube, that means we get 2, and previously it was already having 2, so that is why we get 2. So, you can write like this, 0 plus 2 by 1, right, 0 plus 2 by 1 equal to 2, and 2 into 2 is 4. Now, what is the value of Ka, because I have to calculate the transmission efficiency. So, we have calculated this value Sm, and now we have to calculate this Ka, and by comparing this, this is the value of Ka, 1 plus K into Mt, so the Ka is 0.4. Now, the transmission efficiency is 0.4 whole square into 4 divided by 1 plus 0.4 square into 4 into 100, because we have to calculate in percentage, and after solving this we will get answer as 39%. So, correct answer for this particular question is option B, 39%. Next is question number 39. A diode detector load consists of 0.09 microfarad capacitor in parallel with a 5 kilo ohm resistor. The maximum depth of modulation without diagonal clipping at modulating frequency 1000 Hz and 10,000 kilohertz. So, a diode detector, that means envelope detector, and in case of envelope detector we know that the time constant RC should be less than equal to root over 1 minus MA square upon MA into omega m. Now, we have to calculate the maximum depth of modulation, that means the modulation index without diagonal clipping at modulating frequency of 1000 and 1010 kilohertz. So, if we substitute the value of R and C, let us say for modulating frequency, that is Fm equal to 1000 Hertz, if I substitute all the values, R equal to 5 kilo ohm and C equal to 0.01 microfarad, this should be less than equal to root over 1 minus MA square upon MA into 1000, 2 pi into 1000, okay, because this is omega m and we have to write omega 2 pi Fm, it is Fm is given. So, for here this particular equation, if you find, you will get the modulation index, I think 0.95. So, you should get this value, you can check this, I am just telling the answer. And similarly, for Fm equal to 10 kilohertz, just you have to submit the value of Fm here as 10 kilohertz and you will get the value of modulation index as 0.3. So, you can check the answer, whatever will be the answer, the option is given to us. If the answer is different, then that will be one of these option only. I am just writing according to this answer, I have not solved this particular equation, you can solve it. Now, question number 40. Consider the following amplitude modulated signal S of t equal to cos 2000 pi t plus 4 cos 2400 pi t plus cos 2800 pi t. Now, the ratio of the power of the message signal to the power of carrier signal. So, as we know that if all the equation, all the terms in this particular AM signal is in the cosine form, so it means that it is a single tone sinusoidal modulating signal, the AM signal for single tone sinusoidal modulating signal. And whenever this particular single tone sinusoidal modulation comes, the expression is AC 1 plus MA cos omega MT into cos omega CT. So, AC cos omega CT, and if we expand it, we get AC MA by 2 cos omega C plus omega MT and AC MA by 2 cos omega C minus omega MT. So, there is a 3 term out of which the 2 is having same amplitude and they are sideband terms. So, this is our upper sideband and this is our lower sideband and having the same amplitude AC MA by 2, and in the given expression it is having amplitude 1 and the last term is also having amplitude 1. It means one of these will be lower sideband and other will be upper sideband, and the remaining term will be carrier frequency. It means that this is a carrier term and the frequency component higher than carrier is upper sideband. So, this is 2400 pi, this is 2800, that means this is a upper sideband, and this is less than 2400, that means it is a lower sideband. So, now we can compare and can find the value of carrier amplitude. So, this is the carrier term, this is also the carrier term. So, on comparing we get the carrier amplitude as 4. So, first thing we can calculate is AC equal to 4. And second, on comparing this lower sideband, we get AC MA by 2, we get AC MA by 2 equal to 1, that means MA equal to 2 by AC, that is 2 by 4, or you can say 0.5. So, modulation index is 0.5. Now, we know that the message signal in case of AM lies in the sideband. So, here it is asked that the ratio of power of the message signal, the ratio of power of message signal, and message signal lies in the sideband, it means the power of sideband. Whenever it is asked that the power of message signal in case of AM, so actually it is asking that the power in sideband. So, power of message is power in sideband because message lies in sideband. So, power in sideband is PSB and it is equal to PCMA square by 2. Power in sideband PCMA square by 2, and we have to calculate the ratio of sideband power to carrier power, and we know that for single tone modulation, it is equal to MA square by 2 because this PC will be in the denominator, then we get MA square by 2 and MA is 0.5 whole square divided by 2 and we get 1 by 8, or you can write 0.125. Up to 3 decimal places it is asked and the correct answer will be 0.125. So, you have to remember this thing whenever the IIT asks for the message signal in case of AM, actually it is asking for the power in sideband.